Hi everyone, I am here back again reading the third edition of Python Programming, An Introduction to Computer Science by John Zelle. Today I'm reading chapter 8. I'm not reading the chapters in order, but I do hope to read them all eventually. Chapter 8 is covering loop structures and booleans, and off we go. Objectives: to understand the concept of definite and indefinite loops as they are realized in the Python for and while statements. To understand programming patterns, interactive loop and sentinel loop, and their implementations using a Python while statement. To understand the programming pattern end of file loop and ways of implementing such loops in Python. To be able to design and implement solutions to problems involving loop patterns, including nested loop structures. And finally, to understand the basic ideas of Boolean algebra and be able to analyze and write Boolean expressions involving Boolean operators. So, section 8.1 for loops, a quick review. In chapter 7, we looked in detail at the Python if statement and its use in implementing programming patterns such as one-way, two-way, and multi-way decisions. In this chapter, we'll wrap up our tour of control structures with a detailed look at loop and Boolean expressions. You already know that the Python for statement provides a kind of loop. It allows us to iterate through a sequence of values for var in sequence new line body. The loop index variable, or var, takes on each successive value in the sequence, and the statement in the body of the loop are executed once for each value. Suppose we want to write a program that can compute the average of a series of numbers entered by the user. To make the program general, it should work for any size set of numbers. You know that an average is calculated by summing up the numbers and dividing by the count of how many numbers there are. We don't need to keep track of all the numbers that have been entered. We just need a running sum so that we can calculate the average at the end. The problem description should start some bells ringing in your head. It suggests the use of some design patterns that you have seen before. We are We are dealing with a series of numbers. They will be handled by some form of loop. If there are n numbers, the loop should execute n number of times. We can use the counted loop pattern. We also need a running total sum. That calls for a loop accumulator. Putting the two ideas together, we can generate a design for this problem. Input the count of the numbers n, initialize the total to 0, loop n number of times, input a number x, add x to total, output average as total divided by n, or /n. Hopefully you see both the counted loop and accumulator patterns integrated into this design. We can translate this design almost directly into a Python implementation. Hashtag average1.py. Definition main, and open parentheses, close parentheses, colon, new line, n equals int, parentheses, input, parentheses, quote, how many numbers do you have, question mark, end quote, end parentheses, new line, total equals 0.0, new line, for I in range, n in parentheses, colon, new line, x equals float, parentheses, input, parentheses, quote, enter a number, arrow, quote, parentheses, close parentheses. New line, total equals total plus x. New line, print, parentheses, quote, \n. The average of the numbers is, end quote, comma, total, /n, in parentheses, new line, main, open parentheses, close parentheses. I hope that was not too complicated. Moving right along, the running total starts at 0, and each number is added in turn. After the loop, the total is divided by n to compute the average. Here is the program in action. How many numbers do you have? Question mark, answer 5. Enter a number, arrow, arrow, 32. Enter a number, arrow, arrow, 45. Enter a number, arrow, arrow, 34. Enter a number, arrow, arrow, 76. Enter a number, arrow, arrow, 45. The average of the numbers is 46.4. Well, that wasn't too bad. Knowing a couple of common patterns, counted loop and accumulator, got us to a working program with minimal difficulty in design and implementation. Hopefully you can see the worth of committing these sorts of programming cliches to memory. Sorry, that is bothering me out the corner of my eye. Section 8.2, indefinite loops. Our averaging program is certainly functional, but it doesn't have the best user interface. It begins by asking the user how many numbers there are. For a handful of numbers, this is okay, but what if I have a whole page of numbers to average? It might be a significant burden to go through and count them up. It would be much nicer if the computer could take care of the counting numbers for us. Unfortunately, as you no doubt recall, the for loop in its usual form is a definite loop, and that means the number of iterations is determined when the loop starts. We can't use a definite loop unless we know the number of iterations ahead of time, and we can't know how many iterations this loop needs until all of the numbers have been entered. We seem to be stuck. The solution to this dilemma lies in another kind of a loop, the indefinite or conditional loop. An indefinite loop keeps iterating until certain conditions are met. There's no guarantee ahead of time regarding how many times the loop will go around. In Python, an indefinite loop is implemented using a while statement. Syntactically, the while is very simple. While, and then in arrows, condition, arrow, colon, new line, arrow, body, arrow, new page. Here, condition is a Boolean expression. Excuse me. Just like in if statements, the body is, as usual, a sequence of one or more statements. The semantics of while is straightforward. The body of the loop executes repeatedly as long as the condition remains true. When the condition is false, the loop terminates. Figure 8.1 shows a flowchart for the while. Notice that the condition is always tested at the top of the loop before the loop body is executed. This kind of structure is called a pre-test loop. If the loop condition is initially false, the loop body will not execute at all. I'll show you figure 8.0, and you can see, hopefully you have the book, and you can see this image and the loops, the loop flowchart. All right, moving on. Here is an example of a simple while loop that counts from 0 to 10. I equals 0, while I is less than or equal to 10, colon, new line, print, and then in parentheses, little I. New line, I equals I plus 1. This code will have the same output as if we had written a for loop like this. For I in range, and then 11 in parentheses, print I in parentheses. Now that the while version requires us to take care of initializing I before the loop and incrementing I at the bottom of the loop body. In the for loop, the loop variable is handled automatically. I don't know if I read that correctly. Hopefully you did. The simplicity of the while statement makes it both powerful and dangerous. Because it is less rigid, it is more versatile. It can do more than just iterate through sequences, but it is also a common source of errors. Suppose we forget to increment I at the bottom of the loop body in the counting example. I equals 0, while I is less than or equal to 10, new line, print I in parentheses. What will the output from this program be? When Python gets to loop I will be 0, which is less than 10, so the loop body executes printing a 0. Now control returns to the condition I is still 0, so the loop body executes again printing a 0. Now control returns to the condition I is still 0, so the loop body executes again printing a 0. You get the picture. This is an example of an infinite loop. Usually infinite loops are a bad thing. Clearly this version of the program does nothing useful. That reminds me, did you hear about the computer scientist who died of exhaustion while washing his hair? The instructions on the bottle said, lather, rinse, repeat. As a beginning programmer, it would be surprising if you did not accidentally write a few programs with infinite loops. It's a rite of passage for programmers. Even more experienced programmers have been known to do this from time to time. Usually, you can break out of a loop by pressing Control-C, holding down the Control key and pressing C. If your loop is really tight, this might not work, and you'll have to resort to more drastic means, such as Control-Alt-Delete on a PC. If all else fails, there is always the trusty reset button on your computer. The best idea is to avoid writing infinite loops in the first place. Section 8.3, Common Loop Patterns. 8.3.1 is interactive loops. One good use of the indefinite loop is to write interactive loops. The idea behind an interactive loop is that it allows the user to repeat certain portions of a program on demand. Let's take a look at this loop pattern in the context of our number averaging problem. Recall that the previous version of the program forced the user to count up how many numbers there were to be averaged. We want to modify the program so that it keeps track of how many numbers there are. We can do this with another accumulator. Call it count. Then start at 0 and increase by 1 each time through the loop. To allow the user to stop at any time, each iteration of the loop will ask whether there is more data to process. The general pattern for an interactive loop looks like this. Set more data to yes. While more data is, quote unquote, yes, get the next data item. New line, process the item. New line, ask user if there is more data. Combining the interactive loop pattern with accumulators for the total and count yields this algorithm for the averaging program. Initializing total to 0.0. Initialize count to 0. Set more data to yes. While more data is yes, input a number x. Add x to total. Add 1 to count. Ask user if there is more data. Output total divided by count. Notice how the two accumulators are interleaved into the basic structure of the interactive loop. Here is the corresponding Python program. Hashtag average2.py. Def main, open parentheses, close parentheses, colon, new line total equals 0.0. New line count equals 0. More data equals quote unquote yes. While more data, open brackets, 0, close brackets, equal to quote unquote y, colon, new line x equals float, open parentheses, input, open parentheses, open quote, enter a number, arrow, arrow. end quote, end parentheses, new line, total equals total plus X, new line, count equals count plus 1, more new line, more data equals input, open parentheses, open quote, do you have more numbers? Open parentheses, yes or no, close parentheses, question mark, end quote, end parentheses, new line, print, open parentheses, quote, backslash n, the average of the numbers is, end quote, comma, total divided by count, end parentheses, or total / count, end parentheses, new line, main, open parentheses, close parentheses. Notice this program uses string indexing, more data, open bracket 0, close bracket 0, to look just at the first letter of the user's input. This allows for varied responses such as yes, why, yeah, etc. All that matters is that the first letter is a Y. Here is sample output from this program. Enter a number, arrow, 32. New line. Do you have more numbers? Open parentheses, yes or no, close parentheses, question mark. Yes. New line. Enter a number, arrow, 45. New line. Do you have more numbers? Open parentheses, yes or no, close parentheses, question mark, why? New line. Enter a number, arrow, 34. New line. Do you have more numbers? Open parentheses, yes or no, close parentheses, question mark, why? New line. Enter a number, arrow, 76. New line. Do you have more numbers? Open parentheses, yes or no, close parentheses, question mark, why? New line. Enter a number, arrow, 45. Do you have more numbers? Open parentheses, yes or no, close parentheses, question mark, nope. New line. The average of the numbers is 46.4. In this version, the user doesn't have to count the data values, but the interface is still not good. The user will almost certainly be annoyed by the constant prodding for more data. The interactive loop has many good applications. This is not one of them. Section 8.3.2, Sentinel loops. A better solution to the number averaging problem is to employ a pattern commonly known as a sentinel loop. A sentinel loop continues to process data until reaching a special value that signals the end. The special value is called the sentinel. At any value, any value may be chosen for the sentinel. The only restriction is that it be distinguishable from the actual data values. The sentinel is not processed as part of the data. Here is a general pattern for designing sentinel loops. Get the first data item. While item is not the sentinel, process the item. Get the next data item. Notice how this pattern avoids processing the sentinel item. The first item is retrieved before the loop starts. This is sometimes called the priming read, as it gets the process started. If the first item is the sentinel, the loop immediately terminates and no data is processed. Otherwise, the item is processed and the next one is read. The loop test at the top ensures this next item is not the sentinel before processing it. When the sentinel is reached, the loop terminates. We can apply the sentinel pattern to our number averaging problem. The first step is to pick a sentinel. Suppose we are using the program to average exam scores. In that case, we can safely assume that no score will be below 0. The user can enter a negative number to signal the end of the data. Combining the sentinel loop with the two accumulators from the interactive loop version yields this program. #average3.py. New line. Def main, open parentheses, close parentheses, colon, new line, total equals 0.0, count equals 0, X equals float, open parentheses, input, open parentheses, open quote, enter a number, open parentheses, negative to quit, end parentheses, arrow, arrow, end quote, end parentheses, new line, while X is greater than equal to 0, colon, new line, total equals total plus X. New line, count equals count plus 1. New line, X equals float, open parentheses, input, open parentheses, open quote, enter a number, open parentheses, negative to quit, end parentheses, arrow, arrow, end quote, end parentheses, new line, print, open parentheses, quote, backslash n. The average of the numbers is, end quote, comma, total, forward slash 4 divided by count, end parentheses, new line, main, open parentheses, close parentheses, new line. Well, now we go back to reading. I have changed the prompt so that the user knows how to signal the end of the data. Notice that the prompt is identical at the priming read and the bottom of the loop body. Now we have a useful form of the program. Here it is in action. Enter a number, open parentheses, negative to quit, end parentheses, arrow, arrow, 32. Enter a number, open parentheses, negative to quit, end parentheses, arrow, arrow, 45. Enter a number, negative to quit, 34. Enter a number, negative to quit, 76. Enter a number, negative to quit, 45. Enter a number, negative to quit, -1. Now the average of the numbers is 46.4. This version provides the ease of use of the interactive loop without the hassle of having to type yes all the time. The Sentinel loop is a very handy pattern for solving all sorts of data processing problems. It's another cliche that you should commit to memory. This Sentinel loop solution is quite good, but there is still a limitation. The program can't be used to average a set of numbers containing negative as well as positive values. Let's see if we can't generalize the program a bit. What we need is a Sentinel value that is distinct from any possible valid number, positive or negative. Of course, this is impossible as long as we restrict ourselves to working with numbers. No matter what number or range of numbers we pick as a Sentinel, it is always possible that some data set may contain such a number. In order to have a truly unique Sentinel, we need to broaden the possible inputs. Suppose that we get the input from the user as a string. We can have a distinctive, non-numeric string that indicates the end of the input. All others would be converted into numbers and treated as data. One simple solution is to have the Sentinel value be an empty string. Remember, an empty string is represented in Python as open quote, end quote, or quotes with no space in between. If the user types a blank line in response to an input or just hits enter, Python returns an empty string. We can use this as a simple way to terminate input. The design looks like this. Initialize total to 0.0. Initialize count to 0. Input data item as a string, comma, X capital STR. While X capital STR is not empty, new line, convert X capital STR to a number, comma, X. New line, add X to total. New line, add 1 to count. New line, input, next data item as a string, comma, X capital STR. New line, output total, / for divide by count. Comparing this to the previous algorithm, you can see that converting the string to a number has been added to the processing section of the Sentinel loop. Translating it into Python yields this program. Here we go. Hashtag average4.py. Def main, open parentheses, close parentheses, colon, new line, total equals 0.0. New line, count equals 0. New line, X capital STR equals input, open parentheses, open quote, enter a number, open parentheses. arrow to the left, enter, arrow to the right. To quit, end parentheses, arrow, arrow, end quote, end parentheses, new line, while, X, capital STR, exclamation point equals open quote, end quote, colon, new line, X equals float, parentheses, X, capital STR, end parentheses. New line, total equals total plus X. New line, count equals count plus 1. New line, X, capital STR equals input, open parentheses, open quote, enter a number. Open parentheses, enter to quit, end parentheses, arrow, arrow, end quote, end parentheses. New line, print, open parentheses, open quote, backslash n, the average of the numbers is, end quote, comma, total, forward slash for divided by count, end parentheses, new line, main, open parentheses, close parentheses. This code does not turn the input into a number via float until after it has checked to make sure the input was not the sentinel, as in quote unquote. Here is an example run showing that it is now possible to average arbitrary sets of numbers. Enter a number, enter to quit. 34, and well, it's enter space. Just hit enter, hit the enter key to quit, right? Enter a number, enter key to quit, 34. Enter a number, enter key to quit, 23. Enter a number, enter the enter key to quit, 0. New line, enter a number, press enter to quit, negative 25. Enter a number, negative 34.4. Enter a number, 22.7. Enter a number, enter to quit, and then it's blank. The average of these numbers is 3.38333 repeating. We finally have an excellent solution to our original problem. You should study this solution so that you can incorporate these techniques into your own programs. Section 8.3.3, file loops. One disadvantage to all of the averaging programs presented so far is that they are interactive. Imagine you are trying to average 87 numbers and you happen to make a typo near the end. With our interactive program, you will need to start all over again. A better approach to the problem might be to type all of the numbers into a file. The data in the file can be perused and edited before sending it to a program that generates a report. This file-oriented approach is typically used for data processing applications. Back in Chapter 5, we looked at reading data from files by using the file object as a sequence in a for loop. We can apply this technique directly to the number averaging problem. Assuming that the numbers are typed into a file, one per line, we can compute the average with this program. All right, here we go again. Hashtag average5.py. New line, def main, open parentheses, close parentheses, colon, new line, file name with a capital N equals input, open parentheses, open quote, while file are the numbers in. What file are the numbers in? Question mark, end quote, end parentheses. New line, in file equals open parentheses, file, capital N name, comma, R in single quotes, end parentheses, new line, total equals 0.0, new line count equals 0, for line in file, colon, new line, total equals total plus float, line in parentheses. New line, count equals count plus 1, new line, print, open parentheses, open quote, backslash n. The average of the numbers is, end quote, comma, total divided by count, end parentheses. New line, main, open parentheses, close parentheses. In this code, the loop variable line iterates through the file as a sequence of lines. Each line is converted to a number and added to the running total. Many programming languages do not have a special mechanism for looping through files like this. In these languages, the lines of a file can be read one at a time using a form of sentinel loop. We can illustrate this method in Python by using read line, open parentheses, close parentheses. Remember, the read line method gets the next line from a file as a string. At the end of the file, read line returns an empty string, which we can use as a sentinel value. Here's a general pattern for an end of file loop using read line in Python. All right, line equals infile dot read line, open parentheses, close parentheses, new line. While line exclamation point equals open quote, end quote, colon, new line, hashtag process line, new line, line equals infile dot read line, open parentheses, close parentheses, or empty parentheses. At first glance, you may be concerned that this loop stops prematurely if it encounters an empty line in the file. This is not the case. Remember, a blank line in a text file contains a single new line character. So we have parentheses, quote, backslash n, end quote, end parentheses. And the read line method includes the new line character in its return value. Since, quote, backslash n, end quote, exclamation point equals, empty quotes, comma, the loop will continue. Here is the code that results from applying the end of file sentinel loop to our number averaging problem. Hashtag average6.py. Def main, empty parentheses, colon, new line, file capital name, capital N in name, equals input, open parentheses, quote, what file are the numbers in, question mark, end quote, end parentheses, new line, in file equals open parentheses, file capital N name, comma, single quotes are, end parentheses, new line, total equals 0.0, new line, count equals 0, new line, line equals infile.readline, empty parentheses, new line, while line, exclamation point equals, empty quotes, colon, new line, total equals total plus float, open parentheses, line, end parentheses, new line, count equals count plus 1, new line, line equals infile.readline, empty parentheses, new line, print, open parentheses, open quote, backslash n, the average of the numbers is, end quote, comma, total, / count, end parentheses, new line, main, empty parentheses. Obviously, this version is not quite as concise as the version using the for loop. In Python, you might as well use the latter, but it is still good to know about the end of file loops in case you're stuck programming in a less elegant language. New section 8.3.4, nested loops. In the last chapter, you saw how control structures such as decisions and loops could be nested inside one another to produce sophisticated algorithms. One particularly useful but sometimes tricky technique is nesting of loops. Let's take a look at an example program. How about one last version of our number averaging program? I promise this is the last time I'll use this example. Footnote, until chapter 11. Oh my goodness. Suppose we modify the specification of the file-based averaging problem slightly. This time, instead of typing the numbers into the file one per line, we'll allow any number of values on a line. When multiple values appear on a line, they will be separated by commas. That's a little confusing with numbers, don't you think? At the top level, the basic algorithm will be some sort of file processing loop that computes a running total and count. For practice, let's use an end of file loop. Here is the code comprising the top level loop. total equals 0.0, count equals 0, line equals infile dot read line empty parentheses, new line, while line exclamation point equals empty quotes, colon, new line, hashtag update total and count for values in line, new line, line equals infile dot read line, open parentheses, close parentheses, empty parentheses, new line, print, open parentheses, open quote, \n, the average of the numbers is, end quote, comma, total, divided by count, end parentheses. Now we need to figure out how to update the total and count in the body of the loop. Since each individual line of the file contains one or more numbers separated by commas, we can split the line into substrings, each of which represents a number. When we need to loop through these substrings, convert each to a number and add it to total. We also need to add 1 to count for each number. Here is a code fragment that processes a line. For x, capital STR, inline dot split, open parentheses, open quote, comma, end quote, end parentheses, colon, new line, total equals total plus float, open parentheses, x, capital STR, end parentheses, new line, count equals count plus 1. Notice that the iteration of the for loop in this fragment is controlled by the value of line, which just happens to be the loop control variable for the file processing loop we outlined above. Knitting these two loops together, here is our program. Hashtag average 7.py, def main, empty parentheses, colon, new line, file name equals input, open parentheses, open quote, what file are the numbers in, question mark, end quote, end parentheses, new line, in file equals open, open parentheses, file name, comma, r inside single quotes, end parentheses, new line, total equals 0.0, new line, count equals 0, new line, line equals infile dot read line, empty parentheses, new line, while line, exclamation point equals empty quotes, colon, new line, hashtag update total and count for values in line, new line for x, capital STR, in line dot split, open parentheses, open quote, comma, end parentheses, no, end quote before you end the parentheses, colon, new line, total equals total plus float, open parentheses, x, capital STR, end parentheses, new line, count equals count plus 1, new line, line equals infile dot read line, empty parentheses, new line, print, open parentheses, open quote, \n, the average of the numbers is, end quote, comma, total divided by count, end parentheses, new line, main, empty parentheses. As you can see, the loop that processes the numbers in a line is indented inside the file processing loop. Well, you can see it if you look in the book. The outer loop, the outer while loop, iterates once for each line of the file. On each iteration of the outer loop, the inner for loop iterates as many times as there are numbers on that line. When the inner loop finishes, the next line of the file is read, and the outer loop goes through its next iteration. The individual fragments of this program are not complex when taken separately, but the final result is fairly intricate. The best way to design nested loops is to follow the process we did here. First, design the outer loop without worrying about what goes inside. Then design what goes inside, ignoring the outer loops. Finally, put the pieces together, taking care to preserve the nesting. If the individual loops are correct, the nested result will work just fine. Trust it. With a little practice, you'll be implementing double, even triple nested loops with ease. Section 8, 8.4, computing with Booleans. We now have two control structures, if and while, that use conditions, which are Boolean expressions. Conceptually, a Boolean expression evaluates to one of two values, false or true. In Python, these values are represented by the literals capital F false and capital T true. So far, we have used simple Boolean expressions that compare two values. For example, while x is greater than or equal to 0. 8.4.1 Boolean operators. Sometimes the simple conditions that we have been using do not seem expressive enough. For example, suppose you need to determine whether 2-point objects are in the same position. That is, they have equal x coordinates and equal y coordinates. One way of handling this would be a nested decision. If p1.getX, empty parentheses, equal to p2.getX, empty parentheses, colon, new line, if p1.get capital Y, empty parentheses, equal to p2.getY, empty parentheses, colon, new line, hashtag points are the same, new line else, colon, new line, hashtag points are different, new line else, colon, new line, hashtag points are different. You can see how awkward this is. Instead of working around the problem with a decision structure, another approach would be to construct a more complex expression using Boolean operations. Like most programming languages, Python provides three Boolean operators. They are and, or, and not. Let's take a look at these three operators and then see how they can be used to simplify our problem. The Boolean operators and or are used to combine two Boolean expressions and produce a Boolean result. Expr and expr, expr or expr. The and of two expressions is true exactly when both of the expressions are true. We can represent this definition in a truth table. Okay, so here I'm going to show you the truth table. Hopefully you see it in your book right there. And now we're going to talk about it, but I'm not going to read it. I'm not going to try to read the chart to you. In this table, the P and the Q represent smaller Boolean expressions, P and Q. Since each expression has two possible values, there are four possible combinations of values, each shown as one row in the table. The last column gives the value of P and Q for each possible combination. By definition, the and is true only in the case where both P and Q are true. That makes sense. The or of two expressions is true when either expression is true. Here's the truth table defining or. It seems quite self-evident, but I will still show it to you. Put it in the middle there. So there's the or set of information. And hopefully you can look at it more closely in your book. The only time the or is false is when both of the expressions are false. Notice especially that or is true when both expressions are true. This is the mathematical definition of or, but the word or is sometimes used in an exclusive sense in everyday English. So math English is different than everyday English. If your mom said that you could have cake or cookies for dessert, she would probably scold you for taking both. The not operator computes the opposite of a Boolean expression. It is unary. It is a unary operator, meaning that it operates on a single expression. The truth table is very simple. There. Let me show it to you. Can you see it? Probably too dark. Very simple information there on that chart. P or not P. Using Boolean operators, it is possible to build arbitrarily complex Boolean expressions. As with arithmetic operators, the exact meaning of a complex expression depends on the precedence rules for the operators. Consider this expression: A or not B and C. How should this be evaluated? Python follows a standard convention that the order of precedence from high to low is not, followed by and, followed by or. So the expression would be equivalent to this parenthesized version: A or, open parentheses, not B, end parentheses, and C, end parentheses, end parentheses. Unlike in arithmetic, however, most people don't tend to know or remember the precedence rules for the Booleans. I get it. I suggest that you always parenthesize your complex expressions in order to prevent confusion. Now that we have some Boolean operators, we are ready to return to our example problem. To test for the collocation of 2 points, we could use an AND operation. So we have if p1.getX, empty parentheses, equal to p2.getX, empty parentheses, and p2.getY, empty parentheses, equal to p1.get, capital Y, empty parentheses, colon. I'm sorry, I capitalized that one and not all the other ones. Don't be confused by me. Look at the book. New line, hashtag points are the same. New line, else, colon, new line, hashtag points are different. Here, the entire expression will only be true when both of the simple conditions are true. This ensures that both X and Y coordinates match for the points to be the same. Obviously, this is much simpler and clearer than the nested ifs from the previous version. Let's look at a slightly more complex example. In the next chapter, we will develop a simulation for the game of racquetball. Part of the simulation will need to determine when a game has ended. Suppose that score A and score B represent the scores of 2 racquetball players. The game is over as soon as either of the players has reached 15 points. Here is a Boolean expression that is true when the game is over. Score A equal to 15 or score B equal to 15. When either score reaches 15, one of the 2 simple conditions becomes true, and by definition of or, the entire Boolean expression is true. As long as both conditions remain false, neither player has reached 15, the entire expression is false. Our simulation will need a loop that continues as long as the game is not over. We can construct an appropriate loop condition by taking the negative of the game over condition. While not, open parentheses, score A equal to 15 or score B equal to 15, end parentheses, colon, new line, hashtag, continue playing. We can also construct more complex Boolean expressions that reflect different possible stopping conditions. Some racquetball players play shutouts, sometimes called a skunk. For these players, a game also ends when one of the players reaches 7 and the other has not yet scored a point. For brevity, I'll use A for score A and B for score B. Here is an expression for game over when shutouts are included. A equal to 15 or B equal to 15 or open parentheses A equal to 7 and B equal to 0 or B equal to 7 and A equal to 0 end parentheses. Do you see how I have added 2 more situations to the original condition? The new parts reflect the two possible ways a shutout can occur, and each requires checking both scores. The result is a fairly complex expression. While we're at it, let's try one more example. Suppose we were writing a simulation for volleyball rather than racquetball. Traditionally, volleyball does not have shutouts, but it requires a team to win by at least 2 points. If the score is 15-14 or even 21-20, the game continues. Let's write a condition that computes when a volleyball game is over. Here is one approach. Open parentheses, A is greater than or equal to 15, and A minus B is greater than or equal to 2, end parentheses. Or, open parentheses, B is greater than or equal to 15, and B minus A is greater than or equal to 2, end parentheses. Do you see how this expression works? It basically says the game is over when Team A has won, scored at least 15 and leading by at least 2, or when Team B has won. Here's another way to do it. Open parentheses, A greater than or equal to 15 or B greater than or equal to 15, end parentheses, and ABS, open parentheses, A minus B, end parentheses, is greater than or equal to 2. This version is a bit more succinct. It states that the game is over when one of the teams has reached a winning total and the difference in the scores is at least 2. Remember that ABS returns the absolute value of an expression. All right, 8.4.2, the Boolean algebra. All decisions in computer programs boil down to appropriate Boolean expressions. The ability to formulate, manipulate, and reason with these expressions is an important skill for programmers and computer scientists. Boolean expressions obey certain algebraic laws similar to those that apply to numeric operations. These laws are called Boolean logic or Boolean algebra. Let's look at a few examples. The following table shows some rules of algebra with their correlates in Boolean algebra. There's a chart here. All right. So we have algebra, A times 0 equals 0, but in Boolean algebra, A and false equal to false. In algebra, A times 1 equals A, but in Boolean algebra, A and true is equal to A. And in algebra, A plus 0 equals A. In Boolean algebra, A or false is equal to A. For these examples, you can see that and has similarities to multiplication, or has similarities to addition, and 0 and 1 correspond to false and true. Here are some other interesting properties of Boolean operations. Anything ORed with true is just true. A or true is true. Both and or distribute over each other. A or B and C is equal to A or B and A or C. A and B or C is equal to A and B or A and C. A double negative cancels out. Open parentheses, not, open parentheses, not A, end parentheses is equal to A. The next two identities are known as De Morgan's law. Open parentheses, not A or B, end parentheses is equal to, open parentheses, not A, end parentheses, and open parentheses, not B, end parentheses, new line, open parentheses, not, open parentheses, A and B, end parentheses is equal to, open parentheses, not A, end parentheses, or, open parentheses, not B, end parentheses. Let's take a look. Notice how the operator changes between and or when the not is pushed into an expression. One nice property of Boolean algebra is that simple identities of this sort can be easily verified with a truth table. Since there are always a finite combination of possible values for the variables, we can systematically list all of the possibilities and compute the value of the expressions. For example, the following table demonstrates De Morgan's first law. And we have a table here, a chart you can study. You can get all the details there of what makes it true and what makes it false. Hopefully you have the book and you're following along. Here, the rows represent the four distinct cases for the variables a and b, and the columns show the truth value of the sub-expressions in the identity. Notice that the bolded columns are identical, thus proving that the identity always holds. An important application of Boolean algebra is the analysis and simplification of Boolean expressions inside programs. For example, let's go back to the racquetball game one more time. Above, we developed a loop condition for continuing the game that looks like this. While not, score A equal to 15 or score B equal to 15, hashtag continue playing. You can read this condition as something like this. While it is not the case that player A has 15 or player B has 15, you continue playing. We're pretty sure that's correct, but negating complex conditions like this can be somewhat awkward, to say the least. Using a little Boolean algebra, we can transform this result. Applying De Morgan's law, we know that the expression is equivalent to this. Not score A equal to 15 and not score B is equal to 15. Remember, we have to change the or to and when distributing the not. This condition is no better than the first, but we can go one step farther by pushing the nots into the conditions themselves. While score A exclamation point equals 15 and score B exclamation point equals 15, new line, hashtag continue playing. Now we have a version that is much easier to understand. This reads simply as while player A has not reached 15 and player B has not reached 15, continue playing. This particular example illustrates a generally useful approach to loop conditions. Sometimes it's easier to figure out when a loop should stop rather than when the loop should continue. In that case, simply write the loop termination condition and then put a not in front of it. An application or two of De Morgan's laws can then get you to a simpler but equivalent version suitable for use in a while statement. Section 8.5, other common structures. Taken together, the decision structure if, along with a pretest loop while, provide a complete set of control structures. This means that every algorithm can be expressed using just these. Once you've mastered the while and if, you can write every conceivable algorithm in principle. However, for certain kinds of problems, alternative structures can sometimes be convenient. This section outlines some of those alternatives. Section 8.5.1, post-test loop. Suppose you are writing an input algorithm that is supposed to get a non-negative number from the user. If the user types an incorrect input, the program asks for another value. It continues to reprompt until the user enters a valid value. This process is called input validation. Well-engineered programs validate inputs whenever possible. Here is a simple algorithm. Repeat, new line, get a number from the user, new line, until the number is greater than or equal to 0. The idea here is that the loop keeps getting inputs until the value is acceptable. The flowchart depicting this design is shown in Figure 8.2. Notice how this algorithm contains a loop where the condition test comes after the loop body. This is a post-test loop. A post-test loop must always execute the body of the loop at least once. I'll show you Figure 8.2. Hopefully you can look at it in your book and analyze that closely. And you see where the loop tests at the end, right? Because it is a post-test loop. Unlike some other languages, Python does not have a statement that directly implements a post-test loop. However, this algorithm can be implemented with a while by quote-unquote seeding the loop condition for the first iteration. Number equals -1, hashtag, start with an illegal value to get into the loop. While number is less than 0, new line, number equals float, open parentheses, input, open parentheses, open quote, enter a positive number, end quote, end parentheses, end parentheses. This forces the loop body to execute at least once and is equivalent to the post-test algorithm. You might notice that this is similar to the structure given earlier for the interactive loop pattern. Interactive loops are naturally suited to a post-test implementation. Some programmers prefer to simulate a post-test loop more directly by using a Python break statement. Executing break causes Python to immediately exit the enclosing loop. Often a break statement is used to leave what looks syntactically like an infinite loop. Here is the same algorithm implemented with a break. While true, new line, number equals float, open parentheses, input, open parentheses, open quote, enter a positive number, end quote, end parentheses, new line, if number greater than equal to 0, break, hashtag, exit, loop if number is valid. The first line may look a bit strange to you. Remember that a while loop continues as long as the expression in the loop heading evaluates to true. Since true is always true, this appears to be an infinite loop. However, when the value of x is non-negative, the break statement executes, which terminates the loop. Notice that I placed the break on the same line as the if. This is legal when the body of the if contains only one statement. It's common to see a one-line if break combination used as a loop exit. I hope you're getting this because, that was complicated. Even this small example can be improved. It would be nice if the program issued a warning explaining why the input was invalid. In the while version of the post-test loop, this is a bit awkward. We need to add an if so that the warning is not displayed for valid inputs. Number equals -1, hashtag, start with an illegal value to get into the loop. While a number is less than 0, new line, number equals float, open parentheses, input, open parentheses, open quote, enter a positive number, end quote, end parentheses, new line, if number is less than 0, new line, print, open parentheses, quote, the number you entered was not positive, end quote, end parentheses. Do you see how the validity check gets repeated in two places? Adding a warning to the version using break only requires adding an else to the existing if. While true, number, new line, number equals float, open parentheses, input, open parentheses, open quote, enter a positive number, end parentheses, end quote, end parentheses, end parentheses. New line, if number less than 0, colon, new line, print, open parentheses, open quote, the number you entered was not positive, end quote, end parentheses. I think I lost my place. Do you see how the validity check gets repeated in 2 places, adding a warning to the version? I went backwards to the existing if. All right, follow me here. While true, colon, new line, number equals float, open parentheses, input, open parentheses, open quote, enter a positive number, colon, end quote, end parentheses, new line, if number is greater than or equal to 0, colon, new line, break, hashtag, exit loop if number is valid, period. New line, else, colon, new line, print, open parentheses, open quote, the number you entered was not positive, end quote, end parentheses. Okay. Section 8.5.2, loop and a half. Some programmers would solve the warning problem from the previous section using a slightly different style. Let's find out. While true, with a capital T, colon, new line, number equals float, open parentheses, input, open parentheses, quote, enter a positive number, colon, end quote, end parentheses, new line, if number greater than or equal to 0, colon, break, hashtag, loop exit. New line, print, open parentheses, quote, the number you entered was not positive, end quote, end parentheses. Here, the loop exit is actually in the middle of the loop body. This is called a loop and a half. Some purists frown on exit in the midst of a loop like this, but the pattern can be quite handy. The loop and a half is an elegant way to avoid the priming read in a sentinel loop. Here is the general pattern of a sentinel loop implemented as a loop and a half. While true, colon, new line, get next data item, new line, if the item is the sentinel, colon, break, new line, process the item. Figure 8.3 shows a flow chart of this approach to sentinel loops. You can see that this implementation is faithful to the first rule of sentinel loops. Avoid processing the sentinel value. Here is figure 8.3. It's a flow chart. Let me turn it this way. Flow chart that shows the loop and a half method. I'd say it's pretty smart. All right. The choice of whether to use break statements or not is largely a matter of taste. Either style is acceptable. One temptation that should generally be avoided is peppering the body of a loop with multiple break statements. The logic of a loop is easily lost when there are multiple exits. However, there are times when even this rule should be broken to provide the most elegant solution to a problem. Section 8.5.3, Boolean expressions as decisions. So far, we have talked about Boolean expressions only within the context of other control structures. Sometimes Boolean expressions themselves can act as control structures. In fact, Boolean expressions are so flexible in Python that they can sometimes lead to subtle programming errors. Consider writing an interactive loop that keeps going as long as the user response starts with a Y. To allow the user to type either an upper or lowercase response, you could use a loop like this. While response, in brackets 0, is equal to quote unquote Y, or response 0 in brackets is equal to quote unquote capital Y, colon. You must be careful not to abbreviate this condition as you might think of it as in English, while the first letter is lowercase y or capital Y. The following form does not work. While response 0 in brackets is equal to lowercase y in quotes or uppercase y in quotes, colon. In fact, this is an infinite loop. Understanding why this condition is always true requires digging into some idiosyncrasies of Python Boolean expressions. You already know that Python has a bool type. Actually, this is a fairly recent addition to the language, version 2.3. Before that, Python just used the ints 1 and 0 to represent true and false. In fact, the bool type is just a quote-unquote special int, where the values of 0 and 1 print as capital F false and capital T true. You can test this out by evaluating the expression capital true plus capital true. We have been using the bool literals capital true and capital false to represent the Boolean values true and false respectively. The Python condition operators, for example, equal to, always evaluate to the value of type bool. However, Python is actually very flexible about what data type can appear as a Boolean expression. Any built-in type can be interpreted as a Boolean. For numbers, ints and floats, a 0 value is considered as false. Anything other than 0 is taken as true. You can see how a value will be interpreted when used as a Boolean expression by explicitly converting the value to type bool. Here are a few examples. Arrow, bool, and open parentheses, 0, close parentheses. New line, capital F false. New line, arrows, bool with 1 in parentheses. New line, capital T true. New line, arrows, bool, 32 in parentheses. New line, capital T true. New line, arrows, bool, parentheses, quote unquote, hello, end parentheses. New line, capital T true. New line, arrows, bool, open parentheses, empty quotes, end parentheses. New line, capital F false. New line, arrows, bool, open parentheses, 1, 2, 3, in brackets, end parentheses. New line, capital T true. New line, arrows, bool, open parentheses, open and closed empty brackets, end parentheses. New line, capital F false. As you can see, for sequence types, an empty sequence is interpreted as false, whereas any non-empty sequence is taken to indicate true. The flexibility of Python Booleans extends to the Boolean operators. Although the main use of these operators is forming Boolean expressions, they have operational definitions that make them useful for other purposes as well. This table summarizes the behavior of these operators. I will show you. We're talking X's and Y's here. Let me see if I can make it straight in the middle. Hopefully you have the book too, and you can see it in your book and follow along. We have the operator being X and Y, and the operational definition: if X is false, return X, otherwise return Y. If the operator is X or Y, the operational definition is: if X is true, return X, otherwise return Y. If the operator is not X, then the operational definition is: if X is false, return capital T true, otherwise return capital F false. The definition of not is straightforward. It might take a bit of thinking to convince yourself that these descriptions of and or faithfully reflect the truth tables you saw at the beginning of the chapter. Consider the expression X and Y. In order for this to be true, both expressions X and Y must be true. As soon as one of them is discovered to be false, the party is over. Python looks at the expression from left to right. If X is false, Python should return a false result. Whatever the false value of X was, that is what is returned. If X turns out to be true, then the truth or falsity of the whole expression turns on the result of Y. Simply returning Y guarantees that if Y is true, the whole result is true, and if Y is false, the whole result is false. Similar reasoning can be used to show that the description of or is faithful to the logical definition of or that was given in the truth table. These operational definitions show that Python's Boolean operators are short-circuit operators. That means that a true or false value is returned as soon as the result is known. In an and, where the first expression is false, and in an or, where the first expression is true, Python will not even evaluate the second expression. Now, let's look at our infinite loop problem. Response 0 in brackets equal to lowercase y in quotes or uppercase y in quotes. Treated as a Boolean expression, this will always evaluate to true. The first thing to notice is that the Boolean operator is combining two expressions. The first is the simple condition, and the second is a string. Here is an equivalent parenthesized version. In parentheses, response 0 in brackets equal to lowercase y in quotes and parentheses, or open parentheses, open quote, capital Y, close quote, close parentheses, and colon. By the operational description of or, this expression returns either capital T true, returned by equal to when response 0 in brackets is lowercase y, or uppercase Y. When response 0 in brackets is not lowercase y, either of these results is interpreted by Python as true. A more logic-oriented way to think about this is to simply look at the second expression. It is a non-empty string, so Python will always interpret it as true. Since at least one of these two expressions is always true, the or of the expression must always be true as well. So, the strange behavior of this example is due to some quirks in the definitions of the Boolean operators. This is one of the few places where the design of Python has a potential pitfall for the beginning programmer. You may wonder about the wisdom of this design, yet the flexibility of Python allows for certain succinct programming idioms that many programmers find useful. Let's look at an example. Frequently, programs prompt users for information but offer a default value for the response. The default value, sometimes listed in square brackets, is used if the user simply hits the Enter key. Here is an example code fragment. Start with a line. Ans equals input, open parentheses, open quote. What flavor do you want? Vanilla in brackets, colon, end quote, end parentheses. New line, if ans, exclamation, equals, empty quotes, colon, new line, flavor equals ants, new line, else, colon, new line, flavor equal, quote unquote, vanilla. Exploiting the fact that the string in ants could be treated as a Boolean, the condition in this code can be simplified as follows. Ants equals input, open parentheses, open quote, what flavor do you want? Vanilla in brackets, colon, end quote, end parentheses, new line, if ants, colon, new line, flavor equals ants, new line, else, colon, flavor equals, quote unquote, vanilla. Here, a Boolean condition is being used to decide how to set a string variable. If the user just hits enter, ants will be an empty string, which Python interprets as false. In this case, the empty string will be replaced by vanilla in the else clause. The same idea can be more succinctly coded by treating the strings themselves as Booleans and using an or. Ans equals input, open parentheses, open quote, what flavor do you want? Vanilla in brackets, colon, end quote, end parentheses. New line, flavor equals ants or quote unquote vanilla. The operational definition of or guarantees that this is equivalent to the if-else version. Remember, any non-empty answer is interpreted as true. In fact, this task can easily be accomplished in a single line of code. line, flavor equals input, open parentheses, open quote. What flavor do you want? Vanilla in brackets, colon, end quote, end parentheses, or vanilla in quotes. I don't know whether it's really worthwhile to save a few lines of code using Boolean operators this way. If you like this style, by all means, feel free to use it. Just make sure that your code doesn't get so tricky that others, or you, have trouble understanding it. Section 8.6, Example, a simple event loop. Back in Chapter 4, I mentioned that modern programs incorporate graphical user interfaces, or GUIs. They're generally written in an event-driven style. The program displays a graphical interface and then waits for the user events, such as clicking on a menu or pressing a key on the keyboard. The program responds by processing the event. Underneath, the mechanism that drives this style of program is a so-called event loop. The basic outline of a GUI-based program is something like this. Draw the GUI, new line, while true, colon, new line, get next event. New line, if event is, quote unquote, quit signal, colon, new line, break. New line, process the event. New line, clean up and exit. Essentially, we have a sentinel loop, here expressed as a loop and a half, where the sentinel is just a special event. For example, hitting the Q key that causes the program exit. As a simple example, consider a program that simply opens up a graphics window and allows the user to change its color by typing different keys. R for red, G for gray, etc. The user can quit at any time by hitting the Q key. We can code this as a simple event loop using get, capital K, key, empty parentheses, to handle the key presses. Here's the code. Hashtag event underscore loop1.py, keyboard driven color changing window. New line, from graphics import asterisks. New line, def main, empty parentheses, colon. New line, win equals capital G graph, capital W win, open parentheses, open quote, color window, end quote, comma, 500, comma, 500, end parentheses. New line, hashtag event loop, colon, handle key presses until user presses the quote unquote Q key. New line, while capital T true, colon, new line, key equals win.get, capital K, key, empty parentheses. New line, if key equal to, quote unquote, Q, colon, hashtag loop exit, new line, break. New line, hashtag process the key. New line, if key equal to, quote unquote, R, colon, new line, win dot set, capital B background, open parentheses, quote unquote, pink, end parentheses, new line, elif key equal to, quote unquote, W, colon, new line, win dot set, capital B background, open parentheses, open quote, white, end quote, end parentheses, new line, elif key equal to, quote unquote, G, colon, new line, win dot set, capital B background, in parentheses, in quotes, light gray, new line, elif key equal to, quote unquote, B, colon, new line, win dot set, capital B background, in parentheses, in quotes, light blue, new line, hashtag exit program, new line, win dot close, empty parentheses, new line, main, empty parentheses. Notice that each time through the event loop, this program will wait for the user to press a key on the keyboard. The line key equals win.getKey with empty parentheses forces the user to type a key in order to continue. A more flexible user interface might allow the user to interact in various ways, say by typing on the keyboard. selecting a menu item, hovering over an icon, or clicking on a button. In that case, the event loop would have to check for multiple types of events rather than waiting for one specific event. To illustrate, let's extend our simple color changing window to include some mouse interaction. Let's add the ability for the user to click the mouse to position and type strings into the window, a sort of souped up version of the click and type example from Chapter 4. When mixing mouse and keyboard control, we immediately run into a problem. We can no longer rely on our workhorse input methods of getMouse and getKey. Do you see why? If we call win.getKey, then the program will pause under the user types a key. What happens if they decide to use the mouse instead? No dice. The program is stalled, waiting for a key press. Conversely, if we issue a call to getMouse, then keyboard input is locked out because the program is waiting for a mouse click. In interface design parlance, we call these modal input methods because they lock the user into a certain mode of interaction. Input is non-modal. Multimodal might be a better term, when the user is in control of how to interact. In our example, we can make the event loop non-modal by using the alternative methods checkKey and checkMouse. These methods are similar to their counterparts, except they do not wait for the user to do something. Consider this statement. Key equals win.checkKey empty parentheses. New line, or no, just back to reading. Python will check to see whether a key has been pressed, and if so, return a string that represents the key. However, it does not wait. If no key has been pressed, checkKey will immediately return an empty string. By examining the value of key, the program can determine whether any key has been pressed without actually stopping to wait for it. Using the check method versions, we can easily sketch out a non-modal event loop. New line, draw the GUI, while new line, while true, colon, new line, key equals check key, empty parentheses. New line, if key is quit signal, colon, break. New line, if key is a valid key, colon, new line, process key. New line, click equals check mouse, empty parentheses. New line, if click is valid, colon, new line, process click. New line, clean up and exit. Take a careful look at this pseudocode. Each time through the loop, the program looks for a key press or a mouse click and handles them appropriately. If there is no event to process, it does not wait. Instead, it just goes around the loop and checks again. When the program seems to be patiently waiting for the user to do something, it is actually busy spinning around and around the loop. As a first step toward our super click and type program, we can revise the color changing window to incorporate this extended event loop. Here we go. Hashtag event underscore loop 2.py -- color changing window. New line from graphics import asterisk new line def handle key open parentheses k comma win end parentheses colon new line if k equal to quote unquote r colon new line win dot set background open parentheses quote unquote pink end parentheses new line elif k equal to quote unquote w colon new line win dot set background open parentheses quote unquote white end parentheses new line elif k equal to quote unquote g colon new line win dot set background open parentheses quote unquote light gray end parentheses new line elif k equals quote unquote b colon new line win dot set background open parentheses, quote unquote, light blue, end parentheses. New line, def, handle click, open parentheses, pt, comma, win, end parentheses, colon, new line pass. New line, def main, empty parentheses, colon, new line, win equals graph win, open parentheses, quote unquote, click and type, comma, 500, comma, 500, end parentheses. New line, hashtag event loop, colon, handle key presses and mouse clicks until the user, hashtag presses the Q key while true, colon, new line, key equals win.check key, empty parentheses, new line, if key equal to quote unquote Q, colon, hashtag loop exit, new line, break, new line, if key, colon, new line, handle key, parentheses, key, comma, win, end parentheses, new line, pt equals win.check mouse, empty parentheses, new line, if pt, colon, new line, handle click, open parentheses, pt, comma, win, end parentheses, new line, win dot close, empty parentheses, new line, main, empty parentheses. Whew. I have used functions here to modularize the program and emphasize how the structure corresponds to the augmented event loop algorithm. Since I have not yet determined exactly what to do with mouse clicks, I defined a handle click function with a body containing a pass statement. A pass statement does nothing. It simply fills in the spot where Python is syntactically expecting a statement to be. That allows me to run and test this program to see that it acts just like the previous version did. Also, look carefully at the conditions I used in the if statements. When there is no input, the check key and the check mouse both return a value that Python interprets as false. For check key, it is an empty string, and for check mouse, it is a special none object. As you learned in the previous section, this allows for a succinct Pythonic way of checking to see whether there was indeed any user interaction. We can just type if key rather than if key exclamation point equals empty quotes colon, and if pt colon rather than if pt exclamation point equals capital N none. Not all programmers use these idioms, but I rather like the way they read. I think of these as saying, if I got the key, or if I got a point, then I have to do something. Now that we have updated our color changing window program with a non-modal event loop, we are ready to add the mouse handling part. We want to enable users to place text in the window. Rather than dealing with a single character at a time using the existing event loop, it will be more convenient to have users actually type into an entry object. So, clicking on the window initiates a basic three-step algorithm. 1. Display an entry box where the user clicked. 2. Allow the user to type text into the box. Typing is terminated by hitting the enter key. 3. The entry box disappears and the typed text appears directly in the window. There is an interesting thing happening in step 2 of this algorithm. We want the text that the user types to show up in the entry box, but we don't want those key presses to be interpreted as top-level commands. For example, typing a Q into the entry field should not cause the program to quit. We need the program to go modal. That is, the program switches to text entry mode until the user types the enter key. This is similar to the familiar situation in GUI applications where a dialog box pops up and forces the user to do some interaction to dismiss the dialog before continuing to use the application. This is known as a modal dialog. How do we make our entry box modal? The answer is just another loop. Inside the main event loop, we nest another loop that consumes all the key presses until the user hits the enter key. Once the enter key is pressed, the inner loop terminates and the program continues on. Here is a code for the updated handle click. Here we go again. New line, def handle click, open parentheses, pt, comma, win, end parentheses, colon. New line, hashtag, create an entry for user to type in. new line, entry equals capital E entry, open parentheses PT, comma, 10, end parentheses, new line, entry, dot, draw, and in parentheses, win. New line, hashtag, go modal, colon, loop until user types enter key. New line, while true with a capital T, colon, new line, key equals win dot get key, empty parentheses. New line, if key equal to quote unquote return, colon, break. New line, hashtag, undraw the entry and create and draw text 0. New line, entry dot undraw, empty parentheses. New line typed equals entry dot get text, empty parentheses. New line, capital T text, open parentheses PT, comma, typed, end parentheses, dot draw, open parentheses, win, end parentheses. New line, hashtag clear. Ignore in parentheses any mouse click that occurred during text entry win.check mouse, empty parentheses. Study this code to make sure you understand how it implements the 3-step algorithm above. One thing to notice is that get key returns return for the enter key. Historically, the enter key is known as a return key. Also, I've structured the modal loop so that it looks very similar to our other key processing examples. Since we are just waiting for return, I could have simplified it to something like this. While win.getKey empty parentheses exclamation point equals quote unquote return colon new line pass. In this version, the body of the loop literally does nothing. The loop just keeps checking the condition until enter is pressed and it becomes false. Then the do nothing loop quits, allowing the program to continue. Either version gets the job done. The second is cleverer, but the first seems more obvious. It's probably best to go with what's obvious over clever. The very last line of the function is necessary to ensure that the text entry is truly modal. Any mouse clicks that may have occurred before the enter key was pressed should just be ignored, since check mouse only returns mouse clicks that have happened since the last call to check mouse. Calling the function here at the end has the effect of clearing any clicks that may have occurred but not yet been checked for. That's it for this example. I would definitely suggest running and studying the final version of this program, event_loop3.py. A couple things you might try are commenting out the check mouse at the end of the handle click and seeing if you can create a situation where the program acts weird as a result. Another good exercise would be a modification that allows the user to cancel text entry at any time by hitting the escape key. In effect, escape becomes another sentinel for the modal loop, but when used, no text object is created. Section 8.7, we're at the chapter summary. This chapter has filled in details of Python loops and Boolean expressions. Here are the highlights. First, a Python for loop is a definite loop that iterates through a sequence. Second, a Python while statement is an example of an indefinite loop. It continues to iterate as long as the loop conditions remain true. When using an indefinite loop, programmers must guard against the possibility of accidentally writing an infinite loop. Number 3, one important use for an indefinite loop is for implementing the programming pattern interactive loop. An interactive loop allows portions of a program to be repeated according to the wishes of the user. Next, a sentinel loop is a loop that handles input until a special value, the sentinel, is encountered. Sentinel loops are a common programming pattern. In writing a sentinel loop, a programmer must be careful that the sentinel is not processed. Next, loops are useful for reading files. Python treats a file as a sequence of lines. So it is particularly easy to process a file line by line using a for loop. In other languages, a file loop is generally implemented using a sentinel loop pattern. Next, loops, like other control structures, can be nested. When designing nested loop algorithms, it is best to consider the loops one at a time. Next, complex Boolean expressions can be built from simple conditions using the Boolean operators and, or, and not. Boolean operators obey the rules of Boolean algebra. De Morgan's law describes how to negate Boolean expressions involving and or. Non-standard loop structures, such as a loop and a half, can be built using a while loop, having a loop condition of true, and using a break statement to provide a loop exit. Next, Python Boolean operators and or employ short circuit evaluations. They also have operational definitions that allow them to be used in certain decision contexts. Even though Python has a built-in bool data type other data types, for example, int, may also be used where Boolean expressions are expected. Next, GUI programs are generally event-driven and implement carefully designed event loops to control user interaction. Interactions are called non-modal when the user is in control of what happens next, and modal when the application dictates what the user must do next. Section 8.8 is quizzing over the chapter. So feel free to do those exercises, chat about them in the comments below. Thank you for being here and reading along with me, and I'll see you in the next one. Bye.